Hello everyone. In this video, we are going to talk about degrees of mobility, steerability, and maneuverability of mobile robots. The material in this video is coming from this amazing book, Introduction to Autonomous Mobile Robots by Sigward, Nurbach, and Scaramuzza. This is one of the absolute best books out there for learning about mobile robots. So the material is all from this book. So if we have a mobile robot like this and it has a bunch of wheels, and these wheels could be basically fixed wheels or steerable wheels or omnidirectional or Swedish wheels or anything like that. So, and you have a bunch of them on the circumference of the robot. So we want to quantitatively talk about the constraints that each wheel will have on the motion of the robot. And then from there, we talk about degrees of freedom. Because degrees of freedom is all the robot can move, right? But you have to take away all of those constraints. So it is important to identify, formulate, and count those constraints. So here, let's look at one specific wheel. Doesn't matter, this one, this one, this one, any of them. And the center of the robot that we put the X of the robot and Y of the robot coordinate on the body attached frame, call it point P. So P, for instance, could be this point. And we have the X of the robot and the Y of the robot, which is body attached frame, and it spins with the robot. So let's say in this case, this is XR and YR. But again, remember XR and YR does spin as opposed to XI and YI, which you have outside here, correct? And this one is a fixed frame. This is the inertial frame. So P, if we call it like the center of this, the origin of this frame, then the position of each wheel with respect to the center can be defined by a pair of a radial distance L and an angle, a polar angle alpha. Okay, so we are using polar coordinates here. So L and alpha will determine the location of that wheel. For instance, in this case, for this wheel, if we call this radius R for all of them, right? Then L equals R, right? L equals R. And for this wheel, alpha equals 0. Then for this one, L again equals R, but alpha equals like 120 degrees. For this one, again, L equals R and alpha equals 240 degrees. Okay, so we can use a pair of that. Now, also the radius of each wheel here is shown with the small r, and phi here is the spin angle of the wheel about its own axis. Good? So here, we also need an extra angle beta. And what is beta? So here v is the speed, the forward speed of each wheel in along the or on the wheel plane, we call. So this direction 1 is representing from the top view, this is the wheel plane. And then there is direction 2 that is normal to the wheel, and the angle that is normal to the wheel makes by this radial line that has angle alpha, this extra angle is called angle beta. So this is a 90 degree, there is alpha and beta, and using these parameters, we are going to come up with the constraint equations. Okay, so what do we do? If this wheel is free to move in the XI-YI plane, again, remember you have this inertial frame called XI and YI. And in this frame, you can have 3 types of motion because it is a planar robot. So you can move in the X direction of inertial system, Y, and you can spin. So the speed of the robot in the inertial frame is x dot, y dot, and theta dot, and we can call it xi I dot. Now, please pay attention that here xi is not the twist, okay? Because if you looked at my previous video, xi was already a velocity itself. And so in that notation, xi dot will be like an acceleration. So here, the xi dot is a speed, actually. So the xi dot for my previous notation corresponds to the x dot, where x was the pose and x dot was the velocity, or xi dot in this notation corresponds to the xi in my previous one. So whatever it is, this is the speed, okay? This is the notation of this book, so I want you to not be confused. So this is the speed in the inertial frame. Now I can take this in speed in the inertial frame back to the robot frame, the body attached frame xr, yr, by multiplying it by r of theta, where r of theta, as you can see, is a z rotation but transposed. So this is a rz of theta, and of course transposed, because rz of theta takes you from the new frame, which is robot, back to the inertial frame. If you want to go from inertial to the robot, you have to use the transpose, okay? And that is exactly this one. So this is taking my speeds to the robot. So these are my speeds in the robot base frame, okay? Yes, in the body attached frame. Now, so that is this guy here in this formula. Now, we know that if that's the case, then the xi dot r, or this entity, will have some components, right? It will have some components. Let's talk about the components of it and see how we can project them on the axes 1 and 2, and then compare it against the forward velocity of the wheel, which is the only velocity that the center of the wheel can have, v. And this v, as you know from rolling without a slipping, that should be equal to r phi dot, right? So that is equal to r phi dot, that is v. So we want to compare this xi dot r with v by some projection, and of course they should be equal along both axes. So let's see what we can get. Okay, by the way, the theta here that we talk about is not any of these angles, alpha or beta. Alpha, as I said, is defined in the R frame. So that is each one of these vectors with respect to the R frame. So angle alpha is constant in the R frame, the same with L. These two are fixed values because they are defined in the body attached frame. Okay, and also angle beta 2 for a fixed wheel. For a fixed wheel that does not steer, you can steer it. Beta is constant. For a steerable wheel that this angle changes beta, okay, that is going to be a function of time. But again, for a fixed wheel, beta, alpha, and L, they're all constant. Theta is the angle between R frame and I frame. So right now, theta is 0, but as soon as the robot starts turning like this, theta is defined between R frame and I frame. So let's say this is my robot, second after this, and the wheels go like this. So now this is your R frame, x of R, and this is the original x of I. So this is that angle theta, which is time variable, okay? So I just want you to know which ones are variable, which ones are constant. So, and right now we are talking about a fixed wheel, a wheel that does not steer for the moment. So let's assume for a moment beta is constant. And again, later we can make beta to be time variable, as I said, for the steered standard wheel. So this is a fixed standard wheel. So what we need to do is to draw the velocity components of xi dot r and project them along this axes 1 and 2, see what we get. So what do we have here? Well, the x component of this xi dot r is of course going to be along xr, so this is one of those components. The y component of it is going to be along this, correct? And then we have a component because of theta dots. Which component? Well, because this R frame is spinning with angle theta dot, okay, with angular velocity theta dot, and the center of this wheel is not at the center, it will have a component v equals L times theta dot, correct? V equals R omega in spinning about the center. And that is, of course, going to be perpendicular to this line L. So there will be something like this component, and this is perpendicular to that. So there are three components, this one, and this one. And if you want, we can call them xi dot R1, this is xi dot R2, and this is xi dot R3. These are the three components of the velocity that you get because of moving along xr, yr, and the spin about point P. Now we want to project these three along axes 1 and 2, the wheel, the axis of the wheel, and the plane of the wheel. So this is the wheel axis, axis 2. Okay, so let's do it. Let's practice our trigonometry knowledge, see how much trigs we know, and we're gonna get this formula. So what do we have? Well, this angle here is clearly alpha. So if I want to project my xi dot r, correct, along the one axis, the wheel plane, if I want to project my xi dot r along this axis 1, what angle do I need? Well, let's see what it is that I need to calculate. So the angle I need is this one here. Now, what is this angle? Well, if you look here, this whole thing is 90 degrees. There is alpha and beta, so that angle here is 90 degrees minus alpha minus beta. And I need cosine of that to go along one axis. So this is projection along axis 1. Well, cosine of 90 minus alpha minus beta is sine of alpha plus beta. So that is this component here. Good. So you see, you get that component. Then what? Then we go for xi dot component 2. If I want to project it along axis 1, I have to extend this axis 1 on this side. And the angle I need is this one. Well, what is that angle based on what you know? So here, if you look, you can see that, for instance, this angle is like 90 degrees, correct? And this is beta, right? That is going to make this angle beta. And this is alpha. That is going to make this angle alpha. So again, the total angle between xi dot R2 and the negative side of axis 1 is alpha plus beta. So the projection is going to be cosine of alpha plus beta, but since it's in the negative side, it is going to be negative cosine alpha beta plus beta. Okay, that's for that projection. And finally, what about the xi dot R3? Well, xi dot R3 is actually just theta dot, but the velocity that you have, if you remember, the velocity that you have along axis 3 is basically L times theta dot. And how would you project it along axis 1? Well, as you can see, the angle between this xi dot R3 and the negative of axis 1 is simply beta. And it's in the negative side. So it's going to be negative beta, cosine of beta times the coefficient of theta dot, which is L. So it's going to be negative L times cosine beta. There we go. So these are the, if you project these three components, if you project these three components of velocity by their projections, right, by the cosine of the angle between them and the axis 1, you are projecting all of these velocities along axis 1, and all of these should be equal to what? To this v, which is r times phi dot, or you can bring the r phi dot to the other side and say minus r phi dot equals 0. So this is the rolling without slipping condition for just the most general kind of mobile robot that you can get, where you have alpha, where you have beta, you have L, you have theta, you have R, phi, and everything, right? So this is the kind of most complete thing that you can get for a arbitrary mobile robot with as many wheels as you want in different positions and orientations. This is the rolling without slipping condition. Okay, that's equation number 1. Now for equation number 2, everything has to be projected along axis 2. So here everything is going to be along axis 2, or along the axis of the wheel. Therefore, when we project, the xi dot r is now going to be projected along axis 2. Clearly the angle is alpha plus beta, so it is going to be cosine of alpha plus beta, which is exactly what you can see here. Xi dot r2, the angle of that with axis 2 is this guy here, and that is 90 degrees minus alpha beta. Cosine of that is sine of alpha plus beta, so that is what you can see here. And xi dot 3, if you want to project it along axis 2, remember, first you have to add this L, because this L multiplied by theta dot is going to give you that velocity, and the angle, as you can see, the angle here between xi dot r and x-axis is beta. So between xi dot r3 and your axis 2, clearly, let me clean it up, is this angle here. This is the angle that you need, and this angle is 90 degrees minus beta. So you get cosine of 90 minus beta, which is sine beta. And again, there is an L, so you get L sine beta. So that whole projection times the xi dot in the r, that should be equal to 0. Why? Because your wheels cannot do lateral slide. Your wheel will never move along its axis of the wheel, right? It can never move laterally. So all of that should be equal to 0, and then equation 2 is going to be your second equation. Okay, so that's how we formulate rolling without slipping and no lateral slippage along the wheel plane and the axis of the wheel. Okay, now, so that was, again, this was for a fixed standard wheel where the angle of the wheel cannot change, and that is this beta angle. That beta angle cannot change. Now, if it is a steerable one, then the only difference is beta now can change. So equations 1 and 2 still going to be valid, except beta that you have here is going to be beta of time instead of a constant beta. Good. So that is for what? For a steerable wheel. I'll show you another one for a caster wheel, and then you can develop other ones for Swedish wheels, for omnidirectional wheels, and so on. But I don't want to get into those and make this video long, so I just show you one extra one about caster wheel. And the reason I do that is I did not talk much about caster wheels in any of my previous videos on this playlist, because I have one full video I talked about the Swedish wheels. Okay, but I never talked about the caster wheel. So let's see what the caster wheel is and how we formulate the constraint for it, and then we go from there to defining these degrees of manipulability, the maneuverability, steerability, and mobility. So caster wheel, what's the difference? A caster wheel, if you look at it from the top or you look at it from the side, the axis, the vertical axis of it, and the axis of rotation, they are not on the same line, right? So this is the axis about which this wheel goes like this, and this is the axis about which the tire goes with angle phi. So there is an offset that you show by d, or if you look at it from the top, you can see this d as this distance here. And you can see this caster wheel in lots of different places. For instance, if you look at a computer chair or office chair, you can see that here, right? So if you look at this and zoom in, you see the axis is about there and the center is about here. There is a little bit of offset, or you can see it better here that, for instance, this is the axis and the center is there. Again, there is some offset, okay? So if you look at all of them, there is a little bit offset, and this is a caster wheel. So what's the difference in terms of the equations? Well, if you look at the equation along the plane of the wheel, there is no difference. So in this direction, there is no difference. Now let me bring this D on this side so we can match it exactly with the previous picture. So let's say this wheel is here and the V is in this direction. So along this axis 1, there is no difference. You get the exact same equation. The only difference is along this axis here, along the axis of the wheel, that basically, if you remember, when we looked at these components here, look. So the projection for xi.1, r1, and r2 along axis 2 came from cosine alpha plus beta and sine alpha plus beta. No difference this time. Now, the v equal r omega term, this L theta dot that you projected, this xi r dot 3 that you projected, there is a little bit difference here. What is the difference here? So let's say I'm rotating this whole system. Let's keep it as a rigid body for the moment. So let's lock angle beta for a moment and consider it like one rigid body and rotate this with angular velocity theta dot. Okay? I want to calculate the velocity of the center along the axis of the wheel. So I want to calculate that v. So clearly that v is going to be basically the distance from this point, normal distance to the center. So if I continue this and if I project this line normal to that, it's this distance, whatever that distance is, I have to multiply it by theta dot to get that v. Now, how much is that? Well, if you look here, this portion of it is d, and then this portion of it from here to here is L, and this angle here is beta, so this is L sine beta. So L sine beta plus D, if multiplied by theta dot, that is going to be the V along axis of the wheel. And that should be equal to what? It should be equal to D times beta dot, because remember, your axis of the wheel spins this time. Beta is not constant. Okay, beta is a function of time, so there is a beta dot here. And D times beta dot, when you allow the center of the wheel to rotate about that vertical axis here, you allow it to spin with beta dot, then D times beta dot is the result of that. Okay, so you see that, first of all, the component that you had up here as simply L sine beta is this time L sine beta plus D, and the fact that this guy was pure equal to 0 because this beta was fixed. Now, since beta is variable, and not just variable, it has an offset, it creates a velocity d beta dot, and this should be equal to that. Okay, or negative of that in this case. You might say, why don't you have it for a fixed steerable wheel? Because in that one, beta is also variable, so there is a beta dot. The thing is, the center here is spinning about this axis. So, although there is beta dots, the offset of the center about the axis is 0, so there will be no total velocity. So D is 0 in this case for the standard steerable wheel, therefore this is going to be 0. But for a caster wheel, that's not equal to 0. So these are the equations for what? For the caster wheel. These are the equations for the fixed wheel, okay, that is not steerable, these two. And finally, what? For the steerable wheel, which is standard one is the same as equation 1 and 2, except wherever you have beta, it is going to be beta of t. For the caster wheel, basically beta is a beta of t, as well as these extra terms here. And beta again is beta of t. So these are the kind of constraints that you have on the motion of at least 3 of these wheels. Now, let's say we want to come up with a formula for these different degrees of mobility, steerability, and so on. So how do we formulate it? So let's say your robot has a total of n standard wheels, where nf of them are fixed ones and ns of them are steerable ones. So for now, let's just focus on steerable and fixed standard wheels. Okay? Yep. Now, beta f we use to show the orientation of the fixed wheels, and these are constants. On the other hand, beta s of t, we show it to show the variable steering angle of steerable standard wheels. Okay? Yes? Now, if the spin of these wheels are shown by phi f of t and phi s of t, the spin about their own axis, and then if you create an aggregate matrix phi of t, which is phi f of t and phi s of t, then we can combine these equations that you had, like 1 and 2, or basically 3 and 4, or anything like that. We can combine them into a matrix format like this. For if you want to look at the rolling constraint of all wheels, you can put them in a format like that. Well, where does that come from? So for that, we need to compare it against this one, against this equation 1. So for simplicity here, I'm going to copy this, and let's see if I can bring it down here, put it side by side with this so we can compare, and we see where this equation 6 is coming from. So what do we have? This is the equation I have for the fixed wheels and the steerable wheels. They all look alike, except, as I said, beta could be variable, beta of s, and for fixed one, it's just beta of f, okay, based on these notations that we assumed. So, and then their phi dots, whether it's phi dots of f or phi dot of s, we can combine it into phi dots now. So this term here, I can write it as r times phi dot. Okay, so I can write it like this. All of these terms, I can combine them into that, and then you can assume that this J matrix here is basically going to be something made from the radii of the wheels, okay? And then what about the left side? If you look at the left side, this term here, r theta xi dot I, which is this guy, is multiplied by a projection matrix, for a projection vector for that specific wheel. So one wheel will have one row. Now, if you add the second wheel, it will have a second row, a third wheel, a third row. So if you merge all of those rows into a matrix, that is going to be this matrix J1 of beta S. Okay, so this J1 matrix is the projection matrix, and that J2 is basically the matrix of geometry, mostly the radii. So let's talk a little bit more about the dimensions of these matrices, and then we move on to a similar matrix format for the no lateral slip condition. So as I said, J2 is an n by n diagonal matrix whose entries are just radii of the wheels. So this J2 is something like radius of wheel 1, radius of wheel 2, all the way to radius of wheel n, and then everywhere else 0. Okay, so that is J2 because all it needs to form is R. Now J1, as I said, for the fixed wheels, the projection rows all can be combined into J1F, and for the steerable wheels, they will be projected into J1S of beta S. Now you might say, why didn't you say J1F of beta F? Well, you can do that, but remember that beta F is constant. So this J1F is just going to be all a constant submatrix. While this one is variable, this is time variable, because your betas are time variable. So although this is a function of beta F, since all of those beta F's are constant, this is like a constant submatrix. This is like a time variable submatrix. So in this case, J1 of beta S is a matrix with projections for all wheels to their motion along their individual wheel plane. J1 is a constant matrix for all standard wheels. And the dimension is basically for J1F is NF by 3, and for J1 beta S is NS by 3, because you see in each row there are 3 components. So if you have NF fixed wheels and NS steerable wheels, those submatrices are going to be NF by 3 and NS by 3. So the total dimension of this guy is basically going to be NF, right? Or sorry, this one is just NS by 3. This one, as we said, is NF by 3. And this J2 here is simply N by N. Okay, so this is how you can write everything into this matrix format, into this beautiful format. Okay, now as I said, for sliding on the lateral side, the lateral slide, we can have a similar equation. Okay, so for the lateral sliding, if you remember, for fixed wheels or steerable wheels, this was the equation where beta could be constant or variable. And again, if you want, this portion r theta of xi dot times xi dot I is this part here, this projection part, this 3 by 1. You can basically aggregate them for fixed wheels and steerable wheels and combine them into this projection matrix C1 of beta S. And C1 again has a constant submatrix for constant wheels and fixed wheels, and a time variable one for steerable wheels. Okay, so that's the same thing. Now this right hand side is equal to 0, and the dimensions for C1F and C1S are again NF by 3 and NS by 3. Good. Now let's look at this equation 8. This is an interesting equation. What does this equation say? It says this velocity here, which if you remember, was xi dot r, the velocity in the robot attached frame or robot frame, times this matrix times that should be equal to 0. So if this is whatever matrix, let's call it A, and this is whatever velocity, call it V, this is something like A times V equals 0. And if you remember from linear algebra, when A times V equals 0, we say that the vector V belongs to what? Belongs to the null space of matrix A, correct? So V belongs to the null space of matrix A. And if you remember, the dimension in A, the min dimension in A, equals the dimension of the null space plus rank. Remember, so the rank of A plus the dimension of the null space, which you could call nullity of A, was minimum of dimension of A. So if this A was m by n in general, then it would be min of m and n. Good. Now, clearly, the bigger the nullity or the dimension of the null space, the smaller the rank. And rank is the number of independent rows or columns. Yes? Now, in the case of this robot, what does it mean? In this case, this V is all different velocities that you can have in the robot frame. So, the bigger the null space, the bigger the dimension of the null space of A, means there are more directions in which the velocity in those directions could be zero. Okay, and zero motion means a constraint, means you cannot move in that direction. For instance, we'll do it in a second, but for a simple differential drive robot, if you remember, if I call this, for instance, XR and YR, then you know that for a simple differential drive robot, you cannot move sideways. So basically y dot r equals 0. And so this direction here is the direction for the null space. So any vector in this direction, any velocity in this direction belongs to the null space of projection. I'll show you. So there is no motion in that direction, so there is one constraint, and so the only velocities that you can have is really some x dots that you can have plus some theta dots that you can have at any time. So out of the 3 degrees that you can have, one of them is taken, and so you'll define later that the degree of mobility is basically, in this case, is going to be 2, and I'll show you that. And that is the rank of that projection matrix. Okay, so going back here, if you look at this formula 8, that means that these velocities in the R frame, they must belong to the null space of this projection matrix C1 of beta S, and therefore we can define the degree of mobility for a mobile robot as the 3, which is like the maximum dimension that this guy can have, minus a rank of C1 times beta, C1 of beta S, okay? Or the dimension of the null space of it, okay? So in which directions you can have a 0 vector, in which directions you can't. So 3 minus that rank is the degree of mobility. Why do we define it this way? Because based on what I just showed you, the rank of this projection matrix tells us the number of independent constraint. What kind of constraint? No lateral slipping. So it tells us how many independent, no lateral slipping constraints you have, okay? And so we have to take it out of the 3. Why 3? Because we assume here that our robots are planar. So these are planar mobile robots. If they were not planar, then we have to change that number. But if they are planar mobile robots, 3 is the maximum degrees of freedom they can have, and then the number of independent, no lateral sliding, which is rank of this projection matrix, you should subtract to get all possible motions that you can have, okay? And again, I'll show you about the differential drive. You might say, well, not only this guy cannot move, this wheel cannot move to the left, this guy cannot move as well. So why isn't that the rank of that matrix is not 2 and 3 minus 2? Why is the mobility not 1, not 2? Because although there are 2 no sliding conditions, but these 2 align in this case. They are not 2 independent ones. They both count as 1 because they are identical. Okay, if this wheel was here, that would be a different story because they are different lines. But since they are one single line, then they only count as a 1. So rank of the projection matrix, as I'll show you here, is just simply 1. Now, I know if you think like me, you would ask this question. Hey, why did you only, when you define this degree of mobility, why did you only consider this C1 of beta, which came from no lateral slipping? Why did you only consider that why didn't you look into this basically other constraint that you had for rolling without slipping of the tire, right? Because if these are constraints and we are counting them toward reducing the number of degrees of freedom, why don't we count these ones in equations 6 and 7, right? Should we include them as well? The answer is no. Why not? Because although no slipping, rolling without slipping is a constraint, but that does not take away a degree of freedom. Why not? Because let's go back and look here. If you look at this original shape, or this one, doesn't matter. If you look at here, basically, when you say rolling without slipping, yes, you're limiting some entities together, right? You're doing some limitations, but you're not taking that degree of freedom away. All of this projection is not equal to 0. It's equal to some other thing. So although I'm adding a constraint between the velocities in xi, one constraint, but I'm allowing this spin about the axis. So it's like taking 1 degree of freedom away and adding another degree of freedom. Okay? So when the robot, the wheel of the robot can move along this axis 1 with velocity v, and all I'm saying is then these L, alpha, beta, and everything, they should be related to each other as well as phi dot. I'm not really taking away the motion along the direction of the wheel. Okay? You see, I'm not limiting that. But when I say you cannot move in this direction at all, that v equals 0, I'm limiting that lateral motion. But in this longitudinal direction, I'm not limiting it, okay? Because again, as I said, I add a constraint, but this is not equal to 0. There is no null space here. You bring this r phi dot to this side, and all of that constraint equals r phi dot is not equal to 0. There is no nullity here. The rank is full rank, so it is not imposing any limitations to my degrees of freedom. So I just wanted to clarify that for you. Now, with this in mind, let's talk about the 2 other degrees of freedom. One is degree of steerability. So how do we define it? Before I tell you that, I need to talk about a small thing. What is it? This degree of mobility I just defined for you is actually showing you the degrees of controllable freedom based on the change in the velocities of the wheel. What does it mean? Means, for instance, if I go back to this differential drive again, if I have these 2 different phi dots, correct? So I have phi dot right and phi dot left. Based on what velocities, what spin velocities I pick for them, what kind of motion are allowable. So in this case, if I pick them both to be equal, they can go forward or backward. If I pick them to be equal and opposite, I can have pure rotation. And then if they are not equal, I can have a combination, but I can never have a sideways motion. So I have 2 motions, right? Some v and some omega or theta dots. And these are defining my degrees of mobility, which are achievable by changing the velocities of the wheels. Okay, these are those kind of degrees of freedom that are achievable through those. Now, if you have a steering will allow another impact on the system's degree of freedom, but that is indirect. Why is it indirect? Because if I have a tricycle like that, and instead of going like straight like this, I turn it and put it at this angle, I cannot see the effect of that steering right away as long as these guys are not spinning. So if these guys are not spinning at the moment, that rotation of this steerable wheel to the left or right will give me no motion, so I cannot feel it. But when these guys start to spin, now I can see whether I'm going in this direction or this direction or this direction or where. Okay? So the steerable degrees of freedom, they are only felt after the wheels start to move. That's why we call them indirect, but those degrees of mobility are like active ones because you immediately feel them. So the degree of steerability is defined as the rank of the sub portion of the C1 of beta S, the sub portion of it. Which sub portion? The sub portion that was responsible only for the steerable part. Remember that this, if I go back and look at this C1 of beta S, it has two parts. One part that were all of the rows for fixed wheels, and it has this portion which was all of the rows for steerable ones. So the more steerable wheels you have, the more of these rows you have, and so the rank of the submatrix will be larger. So the rank of the submatrix will tell you how many steerable wheels you have. So by looking at the rank of that, you can get the number of steerable wheels. And why would you not just count the number of steerable wheels? Why would you look at the rank? Because you might say that, huh? You might say, hey, why would you look at the rank? Just count the number of steerable wheels. Because rank will tell you whether these steerings are basically giving you anything independent from each other or they're all the same. For instance, if I go here and I add another one just like this here, and I sync these two together, so when one spins, the other one spins with it too, I can say, hey, look, there are two steerable wheels here, right? There are two of them. I can change them, but guess what? They are not independent from each other. So I cannot say because it's 2, the degree of steerability is 2. It's not. These two, they are in the same line. They are synced. So they are really giving me 1 delta of basically S, not 2. The same goes for this case. Remember here? Here I had 2 no lateral slide condition, but because they are not independent, really the rank of that portion was 1. So 3 minus 1 was 2 in this case, or sorry, in this case, in this one. Okay, so you have to pay attention that what kind of independence you have. That's why it's always good to use rank instead of just counting the wheels. And finally, now that your system, because of the motion of the wheels, can have delta M degrees of freedom for mobility, and because of the steerable wheels, it can have delta S degrees of freedom. If you add these two together, you can finally define what? The degree of maneuverability. So maneuverability is basically everything your robot can do because of the spin of the wheels and because of the steering of the steerable wheels. Okay, so that is called degree of maneuverability. It's sum of the two. So now, to clarify all of this, let's look at these two examples together. So we're going to form those projection matrices. We're going to look at the ranks and everything. And when we have them, we're going to calculate these numbers. So what do we need to calculate? What we need to calculate is literally this matrix, C1 of beta S. If we can calculate that, then we need the rank of that, and then we need the rank of the submatrix of that in order to get delta M, delta S, and sum of them. Now, in the case of a differential drive robot, there is no steering wheel, okay? And if this guy is an omnidirectional wheel, it has no effect on anything, so it's not taking away any degrees of freedom. I can just skip it altogether. If you want, I can make a separate video about Swedish wheels and omnidirectional wheels. I just didn't do it in this video because the video, as you can see, is getting very long. So all that counts are these two in this case. So in this case, the number of fixed wheels is 2 and the number of steerable wheels is 1. Okay? So, sorry, 0. 0. My bad. Okay? So now what we need to calculate is 2 rows here. What we need to calculate is 2 rows of this, no lateral slippage. Okay, and once we have those, guess what? We can form our as you can see here, we can form our C1 of beta S. So the kind of thing that we need is this projection here. So we need this one per each one of these wheels. That's all we need. So let's go ahead and calculate it. So first we go for this one on the right, and let's say this is point P. So here L is each one of these half of the chassis width, and in this case let's calculate alpha and beta for each one of them. So if you know, for a mobile robot, if you looked at my other videos, this is the direction of x of r that we always use, and this is the direction of y of r that we use. Okay, so with that in mind, I want to find alpha for each one of them and beta for each one of them, and L is that same L that you can see here. So what is alpha in this case? Well, it's this line, and the angle of that line from the x-axis, as you can see, is negative 90 degrees. And beta is the angle that the axis of the wheel is making with the radial line. And this is the radial line, that's the axis of the wheel, and it cannot change. So beta is simply 0 in this case. Then we come and look at this wheel. In this case, the radial line here with the x-axis is making a positive 90-degree angle. And again, this radial line, the angle of the axis of the wheel with the radial line is again 0. That's all it is. So if we form this 2 into one matrix for this, for the first one, it is going to be cosine of negative 90 degrees, sine of negative 90 degrees, and 0, because sine of beta is 0. Then we have cosine of positive 90 degrees, sine of positive 90 degrees, and again 0. Okay, and if you calculate these numbers, so these are 0 as well. This is negative 1, this is positive 1. So the matrix that you will get is 0, negative 1, 0, 0, 1, 0. This is what matrix? This is your C1. Okay, so that is your C1, and there is no beta S in this case. Okay, so there is no beta S, there is no steering system. So in this case, this delta S is simply 0, as you expected. Then what's the rank of this matrix? Well, all it has is a rank 1. It has only one separate one. This is rank 1 matrix, correct? You can see it by the number of independent things it has. So it's rank equal 1. So degree of mobility, if you remember, it was 3 minus rank of this. So 3 minus 1 is what? 2. And finally, the maneuverability is sum of these two. So you add them together, and guess what? You will get 2. So a differential drive robot can only maneuver in 2 directions, and we know that is in the XR direction, and that is for omega. Okay, so this is what? This is for a differential drive robot. Now we are going to look at what? We are going to look at a tricycle. This is a little bit more interesting. So that is, again, this guy here is C1. Okay, that is C1, just this matrix here. Right, that is C1 of beta S. But there is no beta S in this case. And C1 of beta, correct? This submatrix here, C1S of beta S in this case is literally empty. There is no such a matrix. Therefore, there is no rank. Rank of it is 0. Now, let's look at the tricycle. That is a little bit more interesting, because not only you have 2 fixed wheels, now you have 1 steerable wheel, and it's always good to look at this scenario here. So again, let's put our center somewhere. So let's again put it here. And so again, this is XR and this is YR. Or sorry, that is XR, this is YR. And again, we can have some dimensions. So if you don't mind, I call them W this time, and this guy I call it H, that distance here. And we are going to calculate that projection row again. Remember that one, cosine alpha, beta, and everything. So we need to have L for each wheel, alpha and beta. So what do we have for this one on the right? That's the same as last time. Your alpha is negative 90 degrees, your beta is 0, and your L is W. Then for this wheel, very similar. Alpha is positive 90 degrees, beta is 0, and L is W. Okay, so these are what you have. And then what about this guy here? For this one, the radial distance L equals H. A is the alpha is the angle between the radial line and the x-axis, which align in this case. So alpha is 0 for this guy. And beta is this angle here, the angle that you can change. So in this case, beta is simply beta S. Okay, it's the angle of this steering wheel that you can have. So if I go ahead and look at that, in this case, I will have, basically, if you look at this, I will have 2 rows for the fixed part and 1 row for the steerable part. Okay, so let's go ahead and form this matrix. So in this case, your C1 is going to be, in row 1, you have cosine of alpha plus beta, and we go with this one first. Beta is 0, alpha cosine of that is, if you remember, these are the exact same thing from last time. So this is going to be 0, negative 1, correct? Because they have fixed. The only thing is, yeah, this one is also 0. So no difference, 0, 1, 0. Now the bottom portion, which is for beta S, let's see what that one becomes. And I write it with a different color. So alpha is 0, but beta is beta S. So this is going to be cosine of beta S. This is going to be sine of beta S. And this is going to be H times sine of beta. Now what? Now what do we have in this case? Okay, so first, the steerable part. This part here is C1S of beta S. Okay, that's the bottom portion based on our notation. The top portion, we call it C1F. So the degree of steerability, delta S, is the rank of this. And clearly, this is 1 row, and the rank of 1 row matrix could be 1. So that's it. That's 1. Delta M is 3 minus rank of whole C1. So I need to find the whole rank of C1. 3 minus that is this. Now, what's the rank of this matrix here? Well, rank is the number of independent columns. Now, in this case, this column here is basically 1 separate column. But if you look at these two, they are not independent from each other, because one column could be an integer multiple, could be a multiple of the other one. All you need is to multiply this by basically cotangent of beta divided by h, and you will get that first column. So rank of this guy is 2 in this case, and therefore delta of mobility is going to be 1, and then 1 plus 1 is, of course, maneuverability in this case is also going to be rank 2. And again, this guy can do the same thing. It cannot laterally move in the y direction, but can steer and can move in the x direction. So you might say, what did this extra steering give it? Well, because this steering really is affecting the theta dot motion, and these two wheels could do the theta dot, so that one did not give it a lot of advantage, unless you can, instead of controlling the theta dot by different phi dot left and different phi dot right, instead of those, you can have both of these to spin at the same rate. So in this case, what you can do is sync those wheels together. So you don't need really a differential drive in this case. You can have them be spinning with the same RPM, exact same RPM. So in this case, this phi dot left and phi dot right, set them to be equal. In that case, the only motion you can have is forward and backward. So in order to get the turning, you can get your theta dot from this motion. So that can give you the whole chassis theta dot. Okay, so you don't really need a differential drive in this case. They can spin together, which makes the mechanism a lot simpler. If these are a differential drive, then you don't need steering. They will overlap. Okay, so the steering can get away that differential drive for you, and using a differential in the back or two separate motors, you can simply have a single motor here and make your mechanism a lot simpler. So hopefully this video was useful to you. You learned some basics about these important degrees of freedom for mobile robots. Stay tuned for further videos, and I'll see you in the next lecture. Thank you.